One of the most intriguing discoveries in modern astronomy is the existence of planets that roam the galaxy without being tethered to any star. These celestial nomads, often referred to as rogue planets or free-floating planets, challenge our traditional notions of what a planet is and how it fits into the cosmic order. Unlike the familiar worlds in our solar system, which orbit the sun in predictable paths, rogue planets traverse the galaxy alone, untethered and invisible except for the faint clues they leave behind. How does such a planet come to be cast out into the darkness of space? There are a few key pathways scientists suspect for how these starless worlds form. First, some rogue planets may have been born alongside stars in the same way our Earth and neighboring planets formed, from a swirling disk of gas and dust surrounding a young star. In the rough-and-tumble environment of a nascent solar system, powerful gravitational interactions can occur, especially when multiple massive bodies are swirling in close proximity. Occasionally, a lower-mass planet can be gravitationally ejected by a larger planet or by interactions with other stars passing nearby. This cosmic expulsion effectively flings the planet into interstellar space, where it begins its solitary journey. Another possibility involves the direct formation of planets without stars at all. In dense regions of molecular clouds, where stars are born, there might be fragments of gas and dust that collapse directly into planetary mass objects, but never accumulate enough mass to ignite nuclear fusion like stars do. In such cases, these objects resemble planets in size and composition, but lack any host star. They are sometimes called sub-brown dwarfs or planetary mass objects, and their existence blurs the line between what we classify as a planet or a failed star. Detecting rogue planets presents unique challenges. Without the bright glow of a parent star to illuminate them or provide a gravitational tug detectable by telescopes, these objects are incredibly difficult to spot. Traditional methods of planet detection, such as noticing a star's wobble or dimming caused by an orbiting planet crossing in front, simply do not work. Instead, astronomers rely on techniques like gravitational microlensing. This phenomenon occurs when a massive object passes between a distant star and Earth, bending and amplifying the star's light due to gravity. If a rogue planet crosses the line of sight at just the right moment, it briefly magnifies the background star's light, signaling the presence of the unseen planet. Microlensing surveys have revealed that our galaxy may host a vast number of these starless wanderers. Some studies estimate that rogue planets could be at least as common as stars themselves, or perhaps even more so. This raises fascinating questions about the variety and distribution of planetary bodies in the Milky Way, and suggests that planet formation and ejection might be common processes throughout cosmic history. Aside from microlensing, infrared observations also provide clues. Rogue planets, especially younger ones, retain heat from their formation and thus emit faint infrared radiation. Space telescopes equipped with sensitive infrared detectors can sometimes pick up this thermal glow, allowing astronomers to identify isolated planetary mass objects in nearby star-forming regions. Understanding more about rogue planets has implications far beyond satisfying curiosity. For one, it informs models of planetary system evolution, shedding light on how dynamic and violent the early stages of planet formation can be. It also expands the possibilities for environments where conditions, though extreme, could exist beyond conventional star-based habitable zones. While the absence of a nearby star makes rogue planets extremely cold and dark, some hypotheses suggest that internal heat sources could warm a planet's interior. For example, radioactive decay of elements or residual heat from gravitational contraction might sustain subsurface oceans of liquid water on sufficiently massive rogue planets. This sparks intriguing, if highly speculative, discussions about potential habitats for life beyond traditional planetary systems. Our knowledge of starless worlds is still in its infancy, yet the pieces of this cosmic puzzle continue to come together. From the turbulent birthplaces of stars to the vast, empty spaces between, rogue planets ask us to reconsider what it means to be a planet and how common these lonely wayfarers might really be. These revelations lead us naturally to examine the physical characteristics of rogue planets, their sizes, compositions, and potential atmospheres. How do these properties compare to those of planets orbiting stars? What determines whether a planet can maintain an atmosphere without the warmth and radiation from a sun? Exploring these factors provides insight into how rogue planets live and evolve in the cold depths of space. Rogue planets come in a variety of sizes, some similar to Earth, others rivaling the giant gas planets like Jupiter or even exceeding them. Because they don't orbit a star, their characteristics can differ markedly from planets within star systems, due in part to what environments shape them and how they maintain physical stability without stellar radiation. Understanding these differences starts with considering their mass and composition. Mass plays a crucial role in a planet's ability to retain an atmosphere. On Earth, our atmosphere is held tightly by gravity, shielded partially from solar wind by the planet's magnetic field. For rogue planets, the absence of a star creates a unique set of challenges. Without continuous radiation pressure or a solar wind environment, atmospheric particles are less likely to be blown away, which might help some retain thick atmospheres longer than one might initially think. Still, the planet's gravity must be strong enough to hold gases in place. Smaller rogue planets could lose lighter gases like hydrogen and helium over time. On the other hand, more massive rogue planets, especially those with thick layers of hydrogen and helium, gas similar to Jupiter and Saturn, could maintain extensive atmospheres for billions of years. These gas giants might resemble isolated mini-stellar objects in several ways. Some scientists speculate that the boundary between large rogue planets and small brown dwarfs, the failed stars that don't quite ignite nuclear fusion, may be blurred. Brown dwarfs generally have masses above about 13 times that of Jupiter, allowing them to fuse deuterium for a brief period, but below the threshold for sustained hydrogen fusion, which defines a true star. While these substellar objects don't orbit stars either, in many ways they share properties with the bigger rogue planets categorized strictly within planetary mass ranges. Another important feature of rogue planets is their internal heat. When planets form, the gravitational energy of their accumulating mass is converted into heat. For rogue planets, this internal warmth is the only significant energy source. Over time, this heat slowly radiates away into space. But inside the planet, especially if it contains heavier radioactive elements, decay processes can continually produce heat. Like Earth's geothermal energy, this heat may keep deep layers of a rogue planet somewhat warm. If the planet is large enough and has sufficient insulating layers, especially thick ice or rock, subsurface oceans of liquid water could persist, trapped beneath thick ice shells. This concept is not merely theoretical. In our own solar system, moons such as Europa and Enceladus, though orbiting a starbound planet Jupiter and Saturn respectively, offer analogs. Both moons maintain subsurface liquid water oceans beneath icy exteriors, sustained by tidal heating generated from gravitational interactions with their giant host planets. A rogue planet losing its star might lack these tidal forces, but could rely more heavily on internal radiogenic heating and residual core heat to sustain similar environments beneath their frozen surfaces. For rogue planets without such heat or sufficient atmospheric insulation, conditions become unimaginably harsh. The surface temperatures can drop to near absolute zero, making their exteriors deep frozen wastelands. Yet even in such extreme conditions, the possibility of internal liquid water expands the concept of habitability beyond the classical Goldilocks zone that depends strictly on sunlight. Understanding atmospheres on rogue planets also brings attention to their probable compositions. Many may harbor thick envelopes of hydrogen and helium, common elements in the protoplanetary disk from which planetary bodies form. In contrast, smaller rocky rogue planets might have thinner atmospheres composed of water vapor, carbon dioxide, methane, or even nitrogen. Outgassing from volcanic activity, if it occurs, could contribute to atmospheric dynamics even without solar input. One interesting question astronomers consider is how weather and atmospheric phenomena might function on a world untethered from a star. Without sunlight, traditional weather patterns powered by solar heating would not arise. But internal heat and residual radioactive decay could initiate convection currents, creating winds and storms within the atmosphere. For example, Strong heat differences between the planet's core and outer layers might generate movement in gases, cycling clouds and precipitation in patterns quite unlike those on Earth but still dynamic. Rogue planets might also occasionally pass through the diffuse clouds of interstellar space. While such encounters would be faint, they could introduce transient interactions with the planet's thin atmosphere, potentially leading to temporary auroras or atmospheric changes initiated by external cosmic radiation or particles. One particularly exciting discovery related to rogue planets is the range of masses these objects can have. Some surveys suggest the existence of rogue planets spanning from super-Earths, a few times Earth's mass, all the way to objects surpassing the mass of Jupiter by several times. Studies involving microlensing events, where the planet's gravitational field bends light from distant stars, help determine masses and distances of passing rogue planets. These events reveal that the rogue planet population might be highly diverse, resulting from various ejection and formation mechanisms. Considering formation origins again is crucial here. Those that once orbited stars, later ejected, might retain compositions similar to their former planetary siblings, including rock, ice, metals, and gases dependent on their location within the previous solar system. In contrast, rogue planets that formed directly in molecular clouds might be richer in primordial gases, perhaps resembling tiny gas dwarfs or low-mass brown dwarfs with significant differences from planets in star systems. Further research into rogue planets also opens questions about their journeys through space. Moving at velocities shaped by the gravitational pushes that ejected them or interactions with other stars and interstellar clouds, these planets could be traveling at speeds ranging from a few kilometers per second up to tens of kilometers per second relative to the galactic center. This motion influences how long an object remains within proximity to certain regions or star clusters, and possibly affects the retention of atmospheres if encountering different environments en route. Thinking on a broader scale, the potential ubiquity of rogue planets in our galaxy has implications that touch several corners of astrophysics. If millions or even billions of these free-floating worlds exist, they could contribute significantly to the galaxy's overall mass, influence the dynamics of star clusters, and even affect the formation and evolution of stars themselves through gravitational interactions. Some theories propose that rogue planets passing near young star systems might inject material, change orbits, or alter planetary system architectures in subtle ways. Since their discovery, astronomers have found examples of planetary mass objects in young stellar clusters and star-forming regions, places where stars and planets both take shape. Their detection, often in the infrared spectrum, confirms that starless planetary bodies form alongside stars or may linger after tumultuous early stellar evolution. In some cases, these objects have masses just below the threshold for brown dwarfs, blurring definitions, but expanding our understanding of the spectrum of celestial bodies. Despite these advances, vast uncertainties remain. We lack comprehensive data on how many rogue planets exist throughout the galaxy, what exact compositions they have, and how their conditions change over billions of years. Developing new observation technologies and techniques will be key to addressing these mysteries. One promising area for future studies involves space telescopes sensitive to mid- and far-infrared emissions. Because rogue planets emit primarily heat from their interiors, searching in these wavelengths can reveal older, cooler planetary mass objects that slipped past current detection limits. Missions like the upcoming James Webb Space Telescope with its infrared capabilities, or proposed future survey satellites specialized for wide-field microlensing and infrared detection, may uncover more rogue planets closer to Earth. From a philosophical perspective, the existence of rogue planets presents a fundamental shift in how we consider planetary systems. Traditionally, planets have been thought of as companions to stars, their properties and behaviors understood largely in relation to their suns. Rogue planets stand apart, offering natural laboratories to study planetary properties free from stellar influences. They challenge astronomers to refine classifications, confront the boundaries between planets and stars, and explore physical phenomena under alien conditions. Altogether, rogue planets are a window into the chaotic processes that govern planetary system formation and evolution. They tell a story of creation and upheaval, where planets born from swirling disks can find themselves cast out to wander the interstellar gulf alone. Through ongoing study, these starless worlds not only enrich our knowledge of the cosmos, but also extend the realm of possibility for worlds quite unlike our own, a testament to the diversity and complexity of the universe we inhabit. Detecting rogue planets poses a formidable challenge for astronomers precisely because these worlds lack a bright, nearby star to illuminate or reveal their presence. Unlike planets orbiting stars, which can often be found through methods like observing dimming of starlight during transits or measuring gravitational wobbles, rogue planets drift in darkness against the backdrop of space. As a result, scientists rely on indirect methods and cutting-edge technologies to identify and study them. One of the most productive techniques has been gravitational microlensing. This phenomenon occurs when a massive object, such as a rogue planet, passes in front of a distant star from our vantage point on Earth. The planet's gravity bends and magnifies the star's light, producing a brief but detectable brightening. By carefully monitoring millions of stars in dense regions like the center of our galaxy, astronomers can catch these fleeting events and infer the presence of unseen objects. Microlensing not only reveals objects too dim to observe directly, but also provides estimates for their mass and distance. Microlensing surveys have uncovered candidate rogue planets with masses comparable to Earth and Jupiter. Though these detections don't reveal detailed characteristics such as surface conditions or atmospheres, they do indicate that such planets are abundant throughout the Milky Way. Statistical analyses from these surveys imply that rogue planets may be as numerous as or even outnumber starbound planets, a surprising realization that reshapes our understanding of the galaxy's planetary census. Beyond microlensing, astronomers have made direct attempts to image rogue planets by searching in the infrared spectrum, where such cold, starless planets emit most of their faint heat. Space telescopes equipped with sensitive infrared detectors can spot the dim glow of young rogue planets still cooling down from their formation heat. Some of the most compelling discoveries come from wide-field surveys of star-forming regions and young clusters, where such objects are warm enough and close enough to detect. Instruments like the Spitzer Space Telescope and ground-based observatories employing adaptive optics have identified planetary mass objects free-floating in these stellar nurseries. These observations have revealed a surprising variety of isolated planetary mass objects in young clusters such as the Orion Nebula and the Taurus region. Some of these free-floating bodies have masses just above or below the range attributed to brown dwarfs, further blurring the lines between planets and failed stars. Their existence raises questions about how formation conditions differ in dense stellar cradles, and whether some rogue planets form on their own, independently of stars, rather than being ejected from established systems. With improvements in technology, astronomers hope to push deeper into understanding rogue planet populations beyond nearby star-forming regions and our galactic neighborhood. One particularly exciting future step is the use of dedicated space missions focusing on microlensing and infrared observations, designed to monitor vast regions of the sky with unprecedented sensitivity. Observing rogue planets at different ages and mass scales would help piece together their evolutionary histories, lifespans, and distribution in various galactic environments. Understanding the habitability potential of rogue planets also invites exploration beyond traditional definitions. When we think about habitability, the starting point is usually a planet's surface temperature or its ability to sustain liquid water driven by sunlight. Rogue planets lacking external heating from a star challenge this convention. Yet, as mentioned before, internal heating mechanisms could create niches where liquid water exists beneath thick ice layers. This possibility opens intriguing questions about the kinds of life that might survive or thrive in such isolated, cold environments. On Earth, life exists in extreme places like deep ocean hydrothermal vents, where conditions resemble some hypothetical environments on rogue planets. No sunlight, high-pressure, chemical energy sources fueling ecosystems. If analogous conditions occur on rogue planets, even without sunlight, life could theoretically develop or persist, reliant on geothermal energy rather than photosynthesis. Though this remains speculative, it expands the notion of where life could emerge in the universe and broadens the search for extraterrestrial biology. Another factor that could influence habitability on rogue planets is the presence of a magnetic field. On Earth and other planets with magnetic shields, this field protects the atmosphere and surface from cosmic rays and charged particles from the solar wind. Rogue planets, moving through interstellar space, encounter various sources of cosmic radiation that might strip away atmospheres or alter surface chemistry if unprotected. A magnetic field generated by a molten core and convecting metallic fluids could help shield these planets, preserving atmospheres and potential habitats within. The presence and strength of such magnetic fields depend on the internal composition and thermal evolution of the planet. Larger, rocky rogue planets with active cores may develop magnetic dynamo effects similar to Earth's, while smaller objects may lack this protection. Understanding this factor is essential when assessing rogue planets' potential to hold onto atmospheres and sustain environments suitable for life. In addition to magnetic fields, the chemistry of a rogue planet's atmosphere could hold clues about its history and present condition. For example, the detection of molecular compounds such as methane, carbon dioxide, or ammonia might suggest ongoing geochemical or possibly biological processes. In star-orbiting planets, these would be influenced by stellar radiation and photochemistry, but on rogue planets, chemical processes could differ significantly, driven instead by internal heat and cosmic ray interactions. While we have not yet developed the tools to analyze rogue planet atmospheres in depth, upcoming missions and advancements in telescope sensitivity may allow spectroscopic observations of even faint, starless objects. Identifying the chemical fingerprints of rogue planet atmospheres would be a significant breakthrough, helping distinguish between planets that formed independently versus those ejected after complex evolution in star systems. Beyond direct observation, computer modeling and simulations play a crucial role in advancing our understanding of rogue planets. Scientists use simulations to study how planetary systems evolve dynamically, how planets become destabilized, and the likelihood of ejection from their parent stars. By recreating these scenarios with varied initial conditions, researchers estimate the frequency of rogue planet formation and characteristics such as mass distribution and velocities. These models also explore how rogue planets' interiors cool over time, how atmospheric retention varies with mass and composition, and the timescales over which subsurface oceans might persist. Such work helps guide observational strategies and interpret the limited data currently accessible. Additionally, simulations addressing the interaction between rogue planets and their interstellar surroundings explore fascinating dynamics. For instance, if a rogue planet passes through a dense molecular cloud, it might accumulate gas or dust, temporarily altering its atmosphere or surface conditions. Conversely, exposure to intense cosmic rays in certain regions could cause long-term chemical changes, influencing potential habitability. The trajectories of rogue planets are also of interest. While many are likely to travel through the galactic disk in relatively stable orbits around the center of the Milky Way, some could move in eccentric paths, occasionally venturing near star systems. Such close encounters might have significant implications for those systems. Gravitational perturbations caused by passing rogue planets could disrupt planetary orbits, trigger comet showers, or cause shifts in asteroid belts. This suggests that rogue planets are not mere cosmic wanderers, but potentially active participants in shaping the evolution of star systems they encounter. In rare cases, a rogue planet passing close to a star system might even be captured gravitationally, turning it into a long-term member of the system. Numerical models show that while capture is infrequent, it could explain some unusual exoplanetary orbits or characteristics observed by astronomers. If planets can switch homes, it challenges our ideas about planetary identity and origin. Interestingly, rogue planets may also inspire technological imagination in human space exploration and astrobiology, although these ideas remain speculative. The potential longevity of subsurface oceans heated from within, far from the stellar influences that challenge habitability on planets orbiting volatile stars, raises the tantalizing question of whether such worlds could harbor life, possibly very different from Earth's, in stable refuges. Detecting biosignatures, chemical indicators of life, on rogue planets would be a significant yet difficult goal, requiring instruments capable of sensing subtle atmospheric clues from great distances. In the broader scope of astronomical research, rogue planets underscore the importance of diversity in planetary environments. Until recently, much of exoplanet study was focused on planets orbiting bright, nearby stars, simply because those are easier to detect. But rogue planets compel us to consider planetary formation and survival beyond the influence of a central star, exploring conditions alien to our solar context. Studying these objects also has implications for cosmology and galaxy evolution. The mass contribution of numerous rogue planets might affect dark matter estimates or influence star cluster dynamics, depending on their numbers and distribution. Though they cannot explain all unexplained cosmic mass, understanding their population offers a piece of the complex galactic puzzle. Rogue planets also broaden discussions about planetary system architectures and instabilities. While our solar system appears relatively stable, many star systems undergo dramatic upheavals after formation, often ejecting planets. These chaotic processes balance the system, influence the survival of terrestrial planets, and lead to the exploding variety of planetary systems observed in the galaxy. Such revelations confirm that planets are not static or permanent fixtures confined to star orbits, but can be dynamic entities experiencing migration, ejection, and even isolation. This dynamism has consequences for understanding planet formation theories, the frequency of Earth-like planets, and where to focus future searches for life. As our detection capabilities continue advancing, with more sensitive telescopes, bigger sky surveys, and innovative techniques, the coming years promise discoveries that will fill in many of the current knowledge gaps. Identifying rogue planets closer to Earth will enable more detailed study, including potential measurement of their temperatures, atmospheres, and even motions in real time. The journey to comprehend rogue planets is ongoing, highlighting the ingenuity and adaptability of astrophysical research. These starless worlds demonstrate that the cosmos holds a multitude of planetary experiences, some untethered, some shining, all contributing to our ever-expanding understanding of the universe and the many forms that planets can take beyond the traditional picture tied to stars. The origins of rogue planets provide crucial insight into their nature and the broader context of planetary system formation. There are two primary hypotheses regarding how these starless travelers come to exist. The first and most widely accepted is that rogue planets are formed within a planetary system, but are later ejected due to gravitational interactions, typically in the early chaotic stages of system evolution. The second hypothesis suggests that some rogue planets might form independently, similar to stars, but on much smaller scales, via direct collapse of gas clouds in interstellar space, without ever being gravitationally bound to a star. When considering the first scenario, young planetary systems are often dynamic and unstable. In their infancy, planets can interact gravitationally with each other, especially if multiple giant planets form in close proximity. Over millions of years, these interactions can result in highly elliptical orbits, collisions, or, relevant to rogue planets, violent ejections. For example, a Jupiter-sized planet could find itself accelerated to escape velocity after a close encounter with another massive planet or star, hurtling it into interstellar space. Computer simulations of planet formation have been pivotal in outlining these processes. They demonstrate that systems forming multiple giant planets, and even systems with dense clusters of smaller planets, can become gravitationally unstable. A high proportion of such systems are projected to lose some planets into the galaxy's depths, contributing significantly to the rogue planet population. This ejection process is consistent with observations of exoplanetary systems exhibiting widely varying architectures, including planets on highly elliptical and inclined orbits that defy simple, orderly models. In the alternative formation pathway, evidence is accumulating that some rogue planets may emerge through a process akin to star formation. Just as stars begin from the gravitational collapse of dense regions within molecular clouds, vast, cold collections of hydrogen gas and dust. Some isolated pockets within these clouds may collapse but not gain enough mass to ignite fusion and become stars. Instead, these pockets might form planetary mass objects outright, complete with atmospheres and potentially internal heat. This possibility blurs the distinction between planets and brown dwarfs, objects sometimes called failed stars because they cannot sustain hydrogen fusion but share characteristics with both stars and planets. Brown dwarfs commonly form in molecular clouds, and the boundary between them and large rogue planets is not sharply defined. For instance, objects a few times the mass of Jupiter detected in star-forming regions complicate categorization. They may be rogue planets or low-mass brown dwarfs, depending on their formation and mass. Determining whether an isolated planet formed by ejection or direct collapse is challenging with current observations. However, certain clues help astronomers infer formation routes. Chemical composition and atmospheric signatures can sometimes reveal past interactions, such as evidence of accreted material from circumstellar disks typically associated with planetary origin, or the presence of elements expected in primordial interstellar clouds. Kinematic studies tracking the object's velocity relative to nearby stars and clouds provide additional context, as ejected planets might display higher relative speeds. Understanding these formation mechanisms also sheds light on the diversity of rogue planets. Those ejected likely reflect the varied planetary system architectures and history, encompassing a range from Earth-sized rocky bodies to gas giants many times Jupiter's mass. Rogue planets born from cloud collapse may often be more massive on average or possess different atmospheric or internal characteristics. After formation, rogue planets face the long journey through interstellar space. Because they lack the radiant energy of a nearby star, they cool over time. Their initial heat, retained from formation, gradually dissipates, leading them to become increasingly faint and difficult to detect. Younger rogue planets, especially those recently ejected or formed in a molecular cloud region, are warmer and glow brighter in infrared observations, making them better candidates for discovery. Over billions of years, however, most rogue planets will become cold, dark objects, effectively black dwarfs in miniature, unless internal heat sources such as radioactive decay or residual gravitational contraction provide sufficient warming. Some gas giants may retain thick hydrogen atmospheres capable of trapping heat, while smaller rocky rogue planets will cool faster. One intriguing consequence of long-term isolation is the potential evolution of subsurface environments. Thick ice shells covering a planet's surface could insulate an interior ocean, thereby preserving liquid water even as surface temperatures plummet. This concept parallels the icy moons in our solar system, like Europa and Enceladus, where heat generated internally supports liquid water beneath an icy crust. On rogue planets, geothermal gradients might maintain these habitats for extended geological periods, although predicting the longevity and stability of such environments requires detailed modeling of planetary interiors. Moreover, this internal heat could also maintain geological activity, for example, volcanism or tectonism, which may be fundamental to the recycling of nutrients and sustaining any putative ecosystems. While direct evidence of such activity on rogue planets remains beyond our current observational reach, it remains an area of active theoretical study given its implications for habitability. Beyond their own characteristics, rogue planets may also play a role in the dynamic ecosystem of the Milky Way. Even as lone travelers, they are components of the galaxy's mass distribution and gravitational landscape. When rogue planets pass near star systems, their gravitational influence may perturb distant comets or asteroids, potentially triggering showers of impacts or even slight orbital shifts in established planets. Though these interactions are brief and relatively rare on a cosmic scale, their cumulative effect over millions of years could influence the evolution of planetary systems. In some fascinating scenarios, gravitational captures are possible. A rogue planet that ventures sufficiently close to a star or stellar cluster under certain velocity and geometrical conditions might be ensnared into a new orbit. While the frequency of such events is estimated to be very low, capture could explain some observed exoplanets with unusual orbits or orbital orientations, inconsistent with standard models of in-place formation. Moving beyond individual rogue planets, comparisons with free-floating objects such as brown dwarfs and planetary mass objects in star-forming regions provide a richer picture. Brown dwarfs, bridging the mass gap between the largest planets and the smallest stars, can be found both isolated and in clusters. Their study offers insights about formation processes similar or related to those behind some rogue planets. Notably, brown dwarfs can retain atmospheres, magnetic fields, and sometimes even disks of dust and gas, which could, even in theory, allow planet formation around them, introducing further complexity to classifications. The identification and study of rogue planets fundamentally challenge traditional definitions in astronomy. The International Astronomical Union, IAU, sets criteria differentiating planets, brown dwarfs, and stars based on mass and formation processes, but the distinctions blur at the edges. Rogue planets sit at this frontier, prompting debates about how to precisely define planets. Is a planet necessarily an object orbiting a star, or can free-floating bodies meeting mass and composition criteria also qualify? How do formation histories weigh in classification? These questions remind us that astronomical categories are human-made constructs designed to organize observations, but might need refining as new discoveries add complexity to our understanding. Future observational missions promise exciting developments in rogue planet research. The Nancy Grace Roman Space Telescope, for example, scheduled for launch in the mid-2020s, will conduct extensive microlensing surveys. Its large field of view and high sensitivity will increase our ability to detect and characterize short-lived lensing events caused by rogue planets, potentially yielding data on their numbers, masses, and distribution with far greater statistical confidence. Similarly, the James Webb Space Telescope, JWST, operational since late 2021, offers unprecedented infrared sensitivity that could enable direct imaging and spectroscopic analysis of rogue planets in nearby star-forming regions. Spectroscopy could reveal atmospheric components such as water vapor, methane, or ammonia, deepening our understanding of physical and chemical properties, and perhaps even identifying biosignature gases if present. Ground-based observatories equipped with adaptive optics and next-generation instruments will complement space telescopes by monitoring targeted regions of the sky, identifying candidate rogue planets, and tracking their motions. The European Southern Observatory's Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, when operational, will provide detailed study capabilities unmatched in resolution and sensitivity. As detection techniques improve, there is also growing interest in searching for smaller rogue objects, Earth-sized and even Moon-sized, which are even more challenging to detect because they emit less heat and produce smaller microlensing signatures. While current surveys focus on Jupiter mass and larger objects, expanding this range is essential to comprehensively understanding the rogue planet population and its implications for planetary system evolution. Beyond detection, the scientific community remains curious about the potential for any form of life on these isolated worlds. Life as we know it depends heavily on energy input, liquid water, and chemical building blocks. Rogue planets devoid of sunlight force us to reconsider energy sources that could sustain life. As previously noted, geothermal energy or chemical energy from the planet's interior could provide viable drivers for biological processes. In Earth's deep biosphere and at hydrothermal vents on the ocean floor, entire ecosystems thrive independently of solar energy, sustained by chemosynthesis, microbes converting chemical compounds into usable energy. If analogous environments exist below rogue planet surfaces, perhaps life could emerge or persist, adapted to such extreme conditions. Though speculative at this stage, exploring these possibilities widens astrobiology's scope. Additionally, rogue planets lacking stellar radiation might suffer less from harmful ultraviolet light or stellar flares, which can disrupt or sterilize surface life on planets close to active stars. In such a context, subsurface refuges shielded by ice could be stable and long-lasting niches for life or prebiotic chemistry. However, any biological processes would face challenges from exposure to cosmic rays and interstellar radiation, which might penetrate thin atmospheres or ice layers. Again, the presence of planetary magnetic fields could be critical for shielding and retaining atmospheres capable of supporting subsurface habitats. Continued interdisciplinary research combining planetary science, astrobiology, and observational astronomy is needed to explore the habitability potential of rogue planets in more detail. Laboratory experiments simulating extreme conditions and chemical reactions are another valuable tool for testing hypotheses about life under such environments. Rogue planets thus not only represent fascinating astronomical objects, but also serve as testbeds for fundamental questions about planet formation, planetary system dynamics, and the possibilities for life beyond sunlight. Their study invites us to expand our imagination beyond the familiar setting of the solar system and consider the wide range of planetary experiences existing in the galaxy. In addition to their intrinsic scientific interest, rogue planets can act as catalysts for technological and methodological innovation. Developing techniques to detect these elusive worlds pushes the boundaries of instrumentation, data analysis, and modeling. For example, the high-precision timing needed to capture microlensing events has driven improvements in telescope design and software algorithms to process vast amounts of data. Moreover, rogue planet research encourages international collaborations and shared data repositories. Since microlensing events depend on precise, comprehensive monitoring of millions of stars in dense regions, sharing telescope time and combining datasets from multiple observatories worldwide ensures better coverage, increasing detection rates and reliability. In considering possible future missions, specialized spacecraft equipped with wide-field infrared detectors could conduct surveys optimized for rogue planet discovery. Concepts for such missions envision monitoring star-forming regions and galactic bulge areas continuously to catch transient events, and build statistical samples that will refine estimates of rogue planet formation rates and lifetimes. As the population of known rogue planets grows, their collective properties may eventually inform broader cosmological studies. Although individual rogue planets contribute little to the galaxy's total mass, their abundance implies a non-negligible role in its structure and dynamics. The cumulative gravitational effects of billions or trillions of such bodies may subtly influence the motion of stars within the Milky Way or the stability of star clusters. Additionally, if rogue planets exist in vast numbers around other galaxies too distant to observe individually, they become part of the cosmic inventory of baryonic matter, ordinary matter composed of protons and neutrons, contributing to refinements in galactic mass calculations. In summary, rogue planets offer an extraordinary glimpse into the diversity and complexity of planetary bodies beyond the conventional confines of starbound worlds. Their study intersects many branches of science, from the mechanics of planetary system evolution and astrophysical detection techniques to the prospects for life and the understanding of our galaxy's makeup. With every new discovery and technological advance, our appreciation deepens for these solitary wanderers, not just as curiosities, but as integral components of the cosmic neighborhood, reshaping our comprehension of how planets form, survive, and possibly harbor life in the universe. The pursuit of rogue planets also brings into focus the challenge of understanding their atmospheres, if such worlds indeed possess them, and what those gaseous envelopes might reveal about their nature. Without a star's warmth and light to influence atmospheric chemistry and dynamics, the composition and behavior of these atmospheres could differ markedly from the familiar planets in our solar system. Studying these differences could help astronomers discern the origins and evolutionary histories of rogue planets. Atmospheric modeling of rogue planets tends to center around several key questions. What gases dominate? How thick are the atmospheres? How do they maintain thermal balance in the coldness of interstellar space? And could these atmospheres persist for billions of years despite the lack of a continuous energy source? On gas-giant rogue planets, thick atmospheres composed primarily of hydrogen and helium are expected to be common, much like Jupiter and Saturn. Such a massive envelope acts as an insulating blanket, trapping heat that slowly leaks from the planet's interior. This internal heat originates from gravitational contraction, a process where the planet gradually shrinks over time, and radioactive decay of elements in the core. The atmosphere can also contain trace amounts of methane, ammonia, water vapor, and other compounds, which absorb and emit infrared radiation, contributing to energy transport. The science of modeling these atmospheres borrows heavily from planetary and brown dwarf studies. For instance, cloud formation is an important factor. Clouds of exotic materials such as silicate or iron dust may form at certain temperatures and pressures, affecting the planet's albedo, reflectivity, and infrared emission. These clouds can influence how the planet cools and how it appears through telescopes, especially in the infrared spectrum. Smaller, rocky rogue planets present a more complex puzzle. Due to their lower gravity, retaining a substantial atmosphere is more challenging without replenishment from volcanic outgassing or comet impacts, both of which would be rare in interstellar isolation. However, an atmosphere akin to that of Mars, thin and tenuous but capable of occasional seasonal variations, is conceivable if the planet has sufficient volatiles and geological activity. Moreover, the question of habitability again arises here. Could a rogue terrestrial planet maintain a thin atmosphere thick enough to support liquid water on or beneath its surface? Without solar radiation, liquid water on the surface is unlikely except in extreme geothermal hotspots. Nonetheless, a planet with an insulating atmosphere rich in greenhouse gases, carbon dioxide, methane, or even molecular hydrogen, might trap enough heat to maintain subglacial oceans or subterranean liquid layers. Intriguingly, hydrogen greenhouse atmospheres have been proposed as a mechanism whereby rogue Earth-sized planets could remain habitable. The tremendous infrared opacity of molecular hydrogen can create a greenhouse effect strong enough to elevate surface temperatures despite the absence of sunlight. While this scenario requires a large hydrogen atmosphere and the planet's gravity to hold it in place, it opens up a broader conceptual space for habitability free from stellar dependence. Instrumentally, characterizing these atmospheres remains difficult. Direct imaging of rogue planets is rare because they are extremely faint and isolated, contrasting with exoplanets observed near bright stars whose light overwhelms the planet's emission. However, when a rogue planet passes in front of a distant star, the phenomenon of gravitational microlensing allows us to infer some properties including mass, but atmospheric characterization through microlensing remains beyond current capabilities. Future instruments, especially the next generation of space telescopes, might enable direct spectroscopy of rogue planets' atmospheres by capturing their faint infrared emissions. Spectral analysis can detect molecular signatures, water, methane, carbon monoxide, and others, that inform us about the planet's temperature, chemical processes, and potential habitability. Rogue planets could also serve as natural laboratories for studying extreme planetary processes. Their isolation removes many variables found in star-orbiting planets, allowing clear focus on intrinsic planetary phenomena such as cooling rates, atmospheric dynamics without stellar radiation, and internal heat sources. For example, by observing a rogue planet's thermal emission over time, scientists can better understand how planetary interiors evolve without external forcing. This knowledge then loops back into understanding planetary system formation and evolution. If, for example, many gas giants are ejected from young systems, then factors influencing ejection rates, disk mass, presence of multiple giant planets, nearby stellar encounters, can be better constrained by studying rogue planet populations. Thus, rogue planet studies reinforce our broader understanding of how common planetary architectures in the galaxy are distributed. Another important aspect concerns the gravitational influence of rogue planets on their surroundings beyond just close encounters with star systems. Because rogue planets have mass, albeit much smaller than stars, their cumulative presence contributes to the galaxy's dark matter in a minor but non-negligible way. While rogue planets are not candidates for dark matter, which remains primarily mysterious and likely non-baryonic, they are part of the galaxy's overall baryonic mass budget, ordinary matter. Estimating the total number and distribution of rogue planets is challenging, but not without progress. Statistical analyses of microlensing events towards dense star fields, like the Milky Way's bulge, suggest that rogue planets may be at least as numerous as stars, or even more so. Some studies estimate that for every star, there could be 1 to 2 rogue planets roaming freely. This hints at a remarkable population, potentially numbering in the hundreds of billions across our galaxy alone. If true, the existence of so many rogue planets forces us to reconsider galactic dynamics on subtle levels. Rogue planets, moving through the galactic disk and halo, can interact gravitationally with interstellar gas clouds and dark matter clumps, adding complexity to the Milky Way's mass distribution and evolution. While the precise impact remains to be quantified, it is an active area of astrophysical research. Beyond the Milky Way, the existence of rogue planets likely extends to other galaxies as well. Although individual rogue planets remain undetectable at such distances, the processes that form them, planetary system instabilities and star-like collapses in molecular clouds, are expected universal phenomena. This universality reinforces the idea that planetary bodies exist in diverse environments, not all tethered to stars. The presence of rogue planets raises philosophical and cultural questions about our place in the cosmos. Traditionally, the idea of a planet invokes a connection to a parent star, providing a source of warmth, light, and energy life depends on. Rogue planets challenge this assumption, representing worlds that exist in solitude, floating endlessly without a star to call home. These starless bodies expand our conception of planetary existence and the possible variations life-supporting conditions might take. Scientific curiosity about rogue planets also intersects with future technological exploration. While current interstellar travel remains the stuff of long-term speculation, dreaming about exploring such worlds outside the solar system engages the imagination. Rogue planets might one day be targets for robotic probes or even crewed missions, given their unique properties and potential for subsurface habitats. In education and public engagement, rogue planets serve as compelling topics to inspire interest in astronomy and planetary science. Their mysterious nature, the challenges in detecting them, and their implications for planetary formation make them ideal examples of how science continuously pushes the boundaries of knowledge. In conclusion, rogue planets and starless worlds offer a fascinating and multifaceted field of study that touches on planetary science, astrophysics, astrobiology, and cosmology. Their detection, characterization, and theoretical modeling continue to advance, fueled by cutting-edge observatories and growing data. These solitary planets, once mere theoretical curiosities, have emerged as vital clues to understanding planetary system dynamics, the diversity of planetary types, and the rich complexity of our galaxy. As research continues, rogue planets will no doubt reveal more surprises, deepening our knowledge of the universe and expanding the horizons of planetary science. One intriguing aspect that follows naturally from the study of rogue planets is how their existence influences our understanding of planetary classification and what truly defines a planet. Traditionally, planets have been characterized as bodies orbiting a star, distinguished from stars themselves by their inability to sustain nuclear fusion. The discovery and growing evidence for vast populations of starless planets pushes astronomers to reconsider this definition, expanding it to include free-floating objects that share characteristics with traditional planets but lack a central star. The International Astronomical Union, IAU, which governs the official nomenclature and classification of celestial objects, faced challenges in categorizing these starless bodies. Should a rogue planet be considered a planet simply because of its mass and composition, or does the lack of a host star alter its fundamental classification? Currently, the working consensus is that these objects fit within the planetary category if they meet mass and formation criteria similar to traditional planets, regardless of their orbital status. Yet distinguishing rogue planets from other substellar objects, such as brown dwarfs, adds complexity. Brown dwarfs are often referred to as failed stars, objects too small to ignite hydrogen fusion but massive enough to initiate limited fusion processes involving deuterium. There is a mass overlap range, roughly between 13 and 80 times the mass of Jupiter, where objects can be hard to categorize decisively. Rogue planets tend to be less massive than this threshold, though formation history is also a key factor. Planets generally form through accretion in a protoplanetary disk around a star, whereas brown dwarfs form more like stars through gravitational collapse of gas clouds. Further complicating this picture, some rogue planets might originate through ejection from such systems after formation, while others could form in isolation through direct collapse. Understanding these differences relies on detailed compositional studies and observations, shedding light on a rogue planet's birth environment, information that high-resolution spectroscopy and precise mass measurements can reveal. Another important direction in rogue planet research involves their potential role as hosts for moons or satellite systems. Although one might assume that such starless worlds would find it difficult to sustain stable satellites, given the lack of an external gravitational anchor, it remains possible. In fact, if a rogue planet was ejected from its host star system, along with moons already in orbit, these satellites might continue to orbit stably around the planet in interstellar space. The dynamics of these miniature systems can provide insight into the stability of orbits in a starless context, letting researchers test models of gravitational interactions in the absence of stellar tides. Moreover, a sizable moon could also augment the potential habitability of a rogue planet. The tidal forces, a gravitational tugging between a planet and its moon, could provide internal heating, similar to how Jupiter's moon Io experiences intense geological activity due to tidal flexing. This heating, known as tidal heating, could help maintain subsurface oceans even without sunlight, expanding the range of environments where life might exist. One of the most scientifically provocative concepts related to rogue planets is their potential to harbor life or prebiotic environments despite extreme isolation. The classical view of habitability focuses on the habitable zone around stars, the range of distances where liquid water can exist on a planet's surface due to stellar warmth. Rogue planets, by definition, do not orbit stars and thus lie outside these traditional habitable zones. However, as discussed earlier, various mechanisms exist whereby rogue planets might retain enough heat internally or through atmospheric insulation to sustain liquid water beneath icy crusts or deep within their interiors. This challenges the star-centric bias in astrobiology that restricts the search for extraterrestrial life to planets orbiting host stars. One particularly compelling analogy comes from moons in our own solar system, such as Europa and Enceladus, which contain subsurface oceans heated by internal tidal flexing despite being far from the sun's warmth. These moons demonstrate that liquid water, and potentially life, can exist in environments shielded from direct stellar energy input. In similar fashion, rogue planethood opens the possibility for extraterrestrial ecosystems powered by geothermal or radiogenic energy sources rather than sunlight. Microbial life forms on Earth thrive in extreme environments without solar energy, around deep-sea hydrothermal vents, beneath the Antarctic ice, or within subterranean rocks, showing that life can adapt to remarkable extremes. Dedicated missions in the future might focus on exploring these analog environments, refining our capacity to identify biosignatures or chemical traces of life in environments where traditional markers like photosynthesis are irrelevant. Understanding how life could arise and persist on rogue planets extends the scope of astrobiology and informs the search for life beyond Earth. From a technological perspective, the hunt for rogue planets is accelerating due to advances in observational methods. Instruments such as the Wide Field Infrared Survey Telescope, WFIRST, recently renamed the Nancy Grace Roman Space Telescope, are expected to significantly enhance microlensing surveys. Microlensing occurs when a massive object passes between Earth and a distant star, bending and magnifying the star's light. Rogue planets, when crossing these lines of sight, cause characteristic, short-duration brightening events that can be distinguished from those caused by stars. This method is particularly valuable because it does not rely on the planet's own light and can detect planets across a wide mass range, including those too faint or cold to observe otherwise. As microlensing surveys accumulate, researchers expect to refine statistical estimates about rogue planet populations and to identify candidates for follow-up studies. On another front, infrared space telescopes equipped with state-of-the-art spectrometers, such as the James Webb Space Telescope, JWST, can observe the thermal emission of rogue planets, capturing detailed spectra that reveal atmospheric composition and thermal structures. Although detecting these faint bodies remains challenging, technological progress continually pushes the limits of what is possible. Additionally, the increasing capability of ground-based telescopes equipped with adaptive optics and dedicated exoplanet imagers provides complementary avenues of investigation. The contrast between a rogue planet's infrared emission and background stars or galactic glow is greater than that for planets near bright stars, making high-contrast direct imaging a viable, albeit demanding, approach. Theoretical modeling of rogue planet interiors and atmospheres is also a critical component of this research frontier. Planetary scientists use complex computational codes incorporating physics, chemistry, and fluid dynamics to simulate heat transport, chemical reactions, and atmospheric evolution under starless conditions. These models help predict measurable properties and guide observational strategies. They also raise fascinating possibilities such as the formation of unexpected chemical species or exotic cloud layers resulting from reduced irradiation and unique temperature-pressure regimes. For example, in the deep atmospheres of gas giant rogue planets, mineral clouds composed of silicates or iron could form layers that shift or thicken as internal heat gradually wanes, influencing infrared emission spectra and planet appearance. Explorations of rogue planets feed into our understanding of the galaxy's rogue population as a whole, comprising not only planets but potentially free-floating smaller bodies. Beyond planets, researchers investigate whether moon-sized, dwarf planet-like, or even asteroid-sized objects roam the galaxy independently. These smaller rogue bodies, often referred to as interstellar minor planets or interstellar objects, like the famous Oumuamua and comet Borisov that visited our solar system in recent years, contribute to the broader picture of isolated celestial travelers. Identifying and tracking these objects deepens knowledge about planetary system evolution. Their trajectories and composition hint at violent processes, collisions, gravitational ejections, and system disruptions that dominate young planetary systems. Such objects could also serve as natural interstellar messengers, carrying material from distant realms and allowing study of cosmic chemistry and mineralogy beyond our neighborhood. Considering travel through the galaxy, one must also address the dynamical behavior of rogue planets over cosmic timescales. Without a star's gravity to hold them in place, rogue planets move through the gravitational fields of the galaxy, influenced by its spiral arms, molecular clouds, dark matter clumps, and passing stars. Their orbits follow unpredictable paths that can stretch across hundreds or thousands of light years. Occasionally, a rogue planet might pass close enough to a star system for temporary gravitational capture or even permanent orbit insertion, although such events are thought to be exceedingly rare. Temporary captures could affect the architecture of planetary systems by introducing new bodies or triggering perturbations, and the capture process itself is a fascinating case study in celestial mechanics. Finally, looking ahead, rogue planets encourage revision of our cosmic census writ large. Knowing how many planets exist throughout the Milky Way and how many wander untethered reshapes models of planetary frequency, evolution, and ultimately the likelihood of diverse planetary environments. The traditional measures of planetary habitability and planet occurrence rates must now accommodate a population of wandering worlds that may outnumber those safely circling stars. This immense population, if confirmed, suggests that planetary formation is a robust and frequent outcome of star formation, with planetary systems regularly losing members to the galaxy. In summary, the discovery and ongoing study of rogue planets challenge and enrich many fields of astronomy and planetary science. They pose fundamental questions about planetary origins, classifications, habitability, and the dynamics of free-floating worlds. Future observations and analyses promise to deepen understanding of these extraordinary, starless worlds, underscoring just how unexpected and diverse planetary existence in the universe truly is.